The spotlight never misses. 10,000 documents sit in this language model's context, about 1,000,000 tokens, and somewhere in its attention, there is always at least one head pointing straight at the correct document. 100% of queries. Then the model opens its mouth to answer, and it gets the question right 0.2% of the time. It knows the answer. It can't say it.
One fact before anything else. This is an AI-made explainer, and both of our voices are AI.
By the end of this video, you'll have the mechanism behind that gap, a specific piece of arithmetic inside every transformer layer that drowns the answer as the context grows, plus the two fixes that recover most of it. And this matters beyond one paper because every serious LLM application today runs on a bolt-on vector database doing the searching. This work, from a Berkeley and UT Austin team including Sewan Min, is the first controlled test of whether the model itself can take that job.
And the case for obviously it can is strong. Context windows hit 1,000,000 tokens. Models ace needle in a haystack tests, hide a magic sentence in a wall of unrelated text, and they find it every time. Vendors put it on the launch slide. So skip the vector database. Dump the corpus into context, ask the model directly. Let it apply judgment instead of geometry. The retriever becomes legacy plumbing.
Except it collapses the moment you test it honestly, and diagnosing that collapse is the entire paper. The needle tests mislead because the needle is lexically distinctive. Finding a red marble in a bowl of white ones tells you nothing about picking the slightly redder marble out of 10,000 red ones. This paper builds its test corpora from hard negatives, documents a strong embedding model thinks look relevant. And a rival model you'll meet later aces the synthetic needle tests, then degrades on real retrieval until it falls behind a simple baseline. Passing needle in a haystack tells you close to nothing about real retrieval ability.
Fine, so the naive version dies. Before the collapse means anything, though, what exactly is being replaced, and why replace something that works?
The incumbent works like this. When an AI assistant searches your documents, it never reads them. A separate embedding model turns each document into a single vector, one point on a huge map, computed once in advance. Your question becomes a point too, and the system grabs whichever documents sit closest. That's dense retrieval, the engine under retrieval-augmented generation. Fast, proven, and structurally limited, because relevance gets reduced to geometric closeness between 2 points. Some questions don't live anywhere sensible on that map, and there are provable limits on what one vector per document can encode. We'll meet a benchmark later that was built around exactly that theorem.
Which is the real motivation, right? Not convenience. A model that reads the corpus can apply whatever notion of relevance the task demands. But this idea isn't new. Google made noise about long-context Geminis subsuming retrieval 2 years ago.
Made noise, yes. Tested, no. Prior evaluations were either proprietary systems with no controlled comparison or re-ranking setups where a real retriever narrows the corpus to a handful of candidates first, and the model just sorts them. Re-ranking dodges the two hard requirements, corpora of millions of tokens, and generalizing to corpus sizes far beyond training, because nobody retrains their retriever every time the document collection grows. So the authors built the honest version themselves, and watching where it breaks is where this gets good.
With a deliberately small model, too.
Just over 500 million parameters. Qwen 3, native context, 32,000 tokens, pushed here past 1 million, 30 times its design limit. They call their system BlockSearch. Every document goes into context wrapped with a random 4-digit code, the query goes at the end, and the model answers by generating the code of the relevant document. The corpus gets processed once into a cache and reused across every query, like a new employee reading the whole company wiki on day 1, then answering questions from notes. During that read, each document only attends within itself, which is what makes million-token processing affordable.
The random codes sound like a throwaway detail. I suspect they're not. Prior recipes numbered the documents in order?
They did. and it's fatal. A model trained on 256 numbered documents has never seen the ID 5000, and it learns spurious ties between a code and a position. Randomize the codes every training step, and the code becomes a pure pointer, nothing to overfit. 2 more moves in one breath. One expensive corpus prefill gets shared across 16 queries worth of training signal, and an on-policy loss fixes a subtle bug. Normal training is learning to drive by watching a perfect driver, while here, the model drives, drifts, and gets corrected along its own path. The payoff: the old position-coded recipe is dead by 5,000 documents. BlockSearch stays above 95% at small scale and keeps meaningful accuracy out to roughly 500,000 tokens, 10 times anything it saw in training.
And then the cliff. At 10,000 documents, the full million tokens, it drops to that 0.2% from the open. The obvious read is capacity. 500 million parameters staring at 1,000,000 tokens, and at some point, it just loses track. That's the folk story behind every long context failure. People literally call it context rot. The model gets confused.
The autopsy says the folk story is wrong, and the autopsy is the densest stretch of this episode. It pays off in the strangest table in the paper, a layer that keeps writing at full volume while its content gets swapped out for noise. 3 things to track, all on screen now. The raw score. For every token in context, the model computes an unbounded compatibility number. How relevant is this to my query? The softmax weight. Those raw scores get converted into shares of a fixed pie that always sums to 100%. And the blend. What a layer passes downstream is a weighted average of information from every token, weighted by those shares. Scores rank, softmax slices. The blend is all anything downstream ever sees.
Then the diagnostic question writes itself. At 1,000,000 tokens, do the raw scores still rank the gold document, the correct one, at the top? If the ranking has decayed, it's a capacity story after all.
They could check directly because they always know which document is gold. So they went head by head, layer by layer, and the ranking was intact, not degraded, intact. At layer 19, at least one attention head puts the gold document's raw score first for 100% of queries, at every corpus size, up to and including 1,000,000 tokens. While the generated answer is right 0.2% of the time, the internal search never fails.
Then I'm missing something, Bella. If some head is holding the correct ranking, why can't a later layer just read the ranking off?
Because no layer ever sees a ranking. It sees the blend, and the blend uses softmax shares, and the softmax-denominator sums over every token in context, relevant or not. This is the spotlight from the cold open. Attention has a fixed 100 watts of total light to hand out. In a room of 500 documents, aimed at the right one, the target glows. Add 9,500 more objects and the aim stays perfect, but the same 100 watts smears across everything, and the target gets a fraction of a watt. Now watch the figure on screen. The gold bar is the share of this layer's output that comes from the correct document. At 500 documents, 91%. At 10,000, 1%. And watch the total height of the output next to it. It barely moves, down about a third. The layer keeps writing into the network at full strength. It's just writing the average of 10,000 distractors instead of the answer.
That last part is the nasty bit. If the signal faded, a later layer might notice something missing. Instead, the layer never goes quiet. It starts confidently saying the average of everything irrelevant, at the same amplitude the answer used to have. Downstream has no cue that a swap happened. So, checkpoint. The model ranks perfectly and still fails because
winning the ranking only guarantees you the biggest slice of the pie, and at 1,000,000 tokens, the biggest slice is 1%. The model stays on target, the averaging drowns it. Which means the fixes shouldn't touch the model's knowledge at all. They should attack the denominator.
3 candidates and one fails in a useful way, right?
The failure first. A learned attention sink, a constant added to the denominator, borrowed from streaming stability work. It barely helps, and the reason is clean. A constant can let an unconfident layer quiet itself down, but it can't fight a denominator that grows with every document you add. The fix that works is almost embarrassingly small. Multiply the raw scores by the logarithm of the corpus size before softmax, a contrast knob. The bigger the crowd, the more you amplify the gaps between scores, and log of n turns out to be just enough to cancel the crowd's growth in the denominator. Because the corpus size is plugged in at inference time rather than learned, it keeps working at sizes the model never trained on. And here's the prediction that makes it a real test. If dilution is the bottleneck, not capacity, one multiplication should resurrect million-token retrieval. It does. On MS Marco, from 0.2% to 16.5%, an 82-fold recovery from a contrast knob.
The second fix is blunter. Clear the room. Run the first 16 layers. Use the model's own mid-network attention scores to shortlist the top 256 documents and finish with only those in context. The shortlist keeps the gold document about 96% of the time. Stack both fixes, and the million-token score edges past the dense retriever, 20.5 versus 20.2, from a model running at 30 times its design limit. It also matches or beats MSA, a concurrent model 7 times larger, trained on much longer contexts, the same MSA that aces the synthetic needle tests. But Bella, look at what routing is. A first stage that narrows candidates, a second stage that reads them closely. That's retrieve, then read, rebuilt inside the model that was supposed to delete it. The authors admit this in so many words. Hold that thought.
Held. And hold a second one with it, Eric. The attention ceiling is 100%, and the best readout recovers about 20%. These fixes mitigate dilution. They don't close the gap, and the authors say that plainly too. Still, matching dense retrieval on dense retrieval's home turf was never the endgame. The real question is whether reading can beat distance on a map at something the map can't do.
That's the benchmark called limit, and it's built on a theorem, not a vibe. There exist combinations of relevance judgments that no one vector per document scheme can represent, however good the embeddings. The test itself is almost silly. Short biographies. Geneva Durbin likes quokkas, river otters, tapirs, Joshua trees, pansies, soy sauce, Cards Against Humanity, and elm trees. Query: who likes Joshua trees? Trivial to state, hostile to geometry, because 1 point per person can't encode every combination of hobbies.
And BlockSearch never trained on anything lexical like this, so it's fully out of distribution. The fixed variants beat the dense retriever at every corpus size by 3 to 4 times at the larger ones. At 5,000 documents, around 850,000 tokens, it's 0.149 versus 0.035. A model a fraction the size of production embedders, winning by multiples on a task embeddings are provably bad at. That's the existence proof this whole agenda needed.
Now the pushback, because the abstract reads sunnier than the tables. 3 things. First, matches dense retrieval means a size-matched, half-billion parameter dense retriever the authors train themselves. Production retrieval stacks run 8 billion parameter embedding models, plus re-rankers, plus lexical search. This paper actually uses one of those big embedders as its teacher. The practical gap is bigger than the headline suggests. Second, the economics. Dense retrieval answers a query with 1 embedding and a nearest neighbor lookup, microseconds against billions of documents. This prefills a million-token cache and runs attention over it, and the paper reports no latency, no memory, no cost. Million-token scale sounds big, until you notice web scale is around 6 orders of magnitude bigger, and nothing in the mechanism closes that. Third, the appendix. On a harder benchmark of abstract similarity, where where the task is to find the math problem with the analogous proof technique. Every variant, fixed or not, scores at or near zero. The Joshua tree's win is a lexical win. Relevance beyond similarity is still a promissory note.
On the economics, I just concede, Eric. The silence on cost is a real hole in anything framed as an alternative to search infrastructure, and I won't pretend otherwise. What I'll defend is the science underneath, those weaknesses bound where you'd deploy this, not what the autopsy found. The dissociation and the dilution mechanisms stand whether or not this ever beats a production stack, and they hand the field a new default hypothesis for long context failures generally.
Even granting that, remember which fix carried the best numbers. Routing wins by rebuilding a retrieval pipeline inside the transformer. Read uncharitably, the paper set out to replace retrieve then read, and ended up demonstrating you can't yet escape it. You can only relocate it.
So go back to the opening pair, 100%, 0.2. At the top of the episode, that was a paradox. Now it reads plainly. The spotlight aims perfectly, and softmax smears its 100 watts across 10,000 documents. The bigger claim, for retrieval at least, long context degradation turns out to be plumbing rather than a capability wall, and plumbing can be fixed.
Drop your side in the comments. One model that reads everything, with attention taught to handle crowds, or retrieve then read forever, outside the model or smuggled back in. The full annotated version is at paperdive.ai, every term tapped to define, with links to limit, SSMax, and the related papers by theme. Housekeeping fast. Script by Anthropic's Claude Fable 5. Bella and I are AI voices from 11 Labs. We're affiliated with neither company. The paper is Drowning in Documents at Million Token Scale, published July 1st, 2026. This episode, July 3rd.
Next time a long context fails on you, which is it? A model that lost the thread, or a model that knows the answer and is drowning on the way to saying it?